Hi, my name is Martins, and in this video we're looking at the programmable logic controller, which is commonly called PLC. Now, have you ever wondered why some people find it difficult to understand the working of the PLC? Well, in this video we're looking at the concept of the PLC, and also we're running a lot of demo, particularly use cases of industrial automation using the FX trainer. So without wasting much time, let's move to the agenda for today. So for the agenda, we have number 1, what is a PLC? Number 2, what are the PLC component system? Number 3, PLC programming devices. Number 4, types of programming used for PLC. Number 5, ladder logic and its convention. Number 6, PLC programming using ladder logic with FX trainer software. So what is a PLC? Now, before the introduction of PLCs, when a particular system is required to work in a particular way, such systems are wired in the manner by which they want the system to operate. And when there's a need for the system to respond differently to the same input signals, such systems have to be rewired. But with the introduction of PLCs, rewiring of system when there's a need to change its operation is no longer necessary. So what is to be done with a PLC is to change the program that has been stored in the memory of the PLC, leaving the connection as it is, and the system responds differently. So the PLC is a form of special computers used for industrial automation particularly. So the PLC is a microprocessor based controller that monitors inputs and outputs to implement functions. Now, these functions could be maybe a logic-based decision, it could be a sequencing operation, it could be a timing operation, it could be a counting operation, or even an arithmetic operation. So the diagram here shows the concept of the PLC, where you have an input device, in this case a switch, and the output device, in this case a light bulb, and here is the PLC itself. Now, the input device is connected to the PLC and the output device is connected to the PLC. Now we see that the input and the output are not connected directly, but they are both connected individually to the PLC. So what the PLC does here is to read the signals from the input device, compare it with the instructions stored in its memory, and communicate the action in form of signals to the output device. So when there's a need for the response to change, all that needs to be done is to change the program or the instruction in the memory of the PLC. Now, what are the PLC component systems? The diagram here shows exactly that. Now we have a processor, we have an output interface, an input interface, a power supply, communication interface, program and data memory, then the programming device. What does this unit, what do they do? For the processor is the CPU of the PLC. What the processor does is interpret the signals from the input devices and carry out control actions according to the program or the instructions stored in the memory, and communicate these decisions in action signals to the output device. So what the processor does basically is to look at the signals from the input devices connected to the input interface, and whatever corresponding action that needs to be done based on the instruction in the memory of the PLC, such signals are being transmitted to the output devices. For the power supply, here we see that the power supply is connected to the input interface, the processor, and the output interface. So what the power supply does is to convert the AC voltage into the low voltage DC necessary for this unit to operate effectively. Now, the programming device. The programming device is the mode by which the instruction from the user is being transmitted to the PLC memory. For the memory unit, that's the program and data memory unit. The program and data memory unit stores two kind of informations. Number one is the program and also the data. So the program memory holds the instruction from the user, while the data memory holds the signals from the input interface and the signals for the output interface. The input and output interface, these are where the PLC receives information from the input device and also communicates signals or actions to the output device. For the communication interface, where there is a battery of PLCs and there's a need to communicate in between these PLCs via a particular network. So the communication interface is being used in this case for these PLCs to communicate over a network, probably where there is a kind of synchronous operation that needs to be done in between some set of PLCs in a particular setting. So that's where the communication interface is being used. Then the PLC programming devices. There are three programming devices that can be used to program a PLC. Number one is the handheld device. Number two is the desktop console. And number three is the personal computer. So for the handheld device, which is being shown in this image here, you have the handheld device, you have the PLC itself. So the program is being written on the handheld device and is being transmitted to the PLC via a particular transmission cable. Now, the disadvantage of the handheld device is that it doesn't have enough memory space, so you can't store a lot of memory, a lot of program in its memory. So it can only hold a limited memory for the PLC program, after which they will be transmitted to the PLC itself. But for the desktop console has the advantage of a monitor, like you can see here, and the normal keyboard that we have on our personal computers. So the advantage here is that a kind of simulation can be done, which can be viewed on the display screen, and also the keyboard is the standard keyboard, so it's easier to write the program, and also it holds more memory compared to that of the handheld device. And the third one is the personal computer, which equally has the screen, has the keyboard, and has a lot of memory space, and also can be used to transfer this program. Maybe it can be copied to a flash drive or to a hard drive or any other device, so it can be transmitted from one point to the other. So that's the advantage of the PLC, of the program the PLC using the personal computer. However, for a personal computer to program a PLC, the software of such PLC must have been installed on such a personal computer. Now, the modes by which a PLC can be programmed. A PLC can be programmed in two modes. It's either it's been programmed in the offline mode or the online mode. For the offline mode, the program is being designed, maybe in some cases simulated, and is being transmitted or copied to the PLC when the PLC is not in running mode. So the program is being done and simulated to check for bugs and sent to the PLC when the PLC is not in run mode. So it's safe in that manner. But for the online programming mode, the program is being edited and implemented on the PLC while the PLC is in running mode. So in this case, to program a PLC in such a manner, one has to be sure that the program has no error, so that there's no malfunction of the entire system or a damage to the system in such a process. For the types of programming used for PLC, there are several programming that are standard methods by which a PLC can be programmed, and all these programming methods are the standards that are given by the International Electrotechnical Commission, that is the IEC 1131-3 in the year 1993. And these programming methods are: number one, the ladder diagram, the instruction list, the sequential flow chart, the sequential function chart. Then you have the structured text and the function block diagram. So these are the methods by which a PLC can be programmed, or the programming methods used for programming a PLC. All of the methods are appropriate. However, you can have preference based on probably your understanding of such programming methods. Now, for the ladder logic and its convention, the common programming method that is being used for PLC is the ladder logic. And the reason is that the ladder logic is not designed to be used by persons with a high-end understanding of programming languages. So it's simple to understand, and that is why it is commonly used to program a PLC. Writing a ladder logic is similar to using logic functions, where you have your AND, your OR, your exclusive OR, your NAND, and your NOR. Then also there is what is called latching. All of this we are going to see in the simulation so that we can understand them in the way by which they are being used. So here we have just diagram showing the idea of these logic functions. For the AND, you must have at least two inputs going into a single output. So for the AND logic, both of the inputs has to have a binary of 1 for the output to have a binary of 1. So the diagram here just shows the function block equivalent of this logic here. So this is function block equivalent of this logic here. So you have the amber sign in this block showing that this is a AND gate or an AND logic. For the NAND, the difference in the NAND is this NOT that is on the output. So whatever it is that is the state of the input for the NAND is the reverse that the output would have. For the OR gate, the OR gate equally have two inputs, at least two inputs into one output, whereby at least one of the inputs must have a binary of 1 for the output to have a binary of 1. And here you have the function block equivalent of this logic, showing a greater than or equal to 1 in this block, showing that this is a OR gate. And the NOR of this OR gate is this NOT that you have to the output. So whatever is the state of the input, whatever NOR, whatever OR output that this should give you, the reverse is what the NOR gate would give. And equally, this is the function block equivalent of this NOR gate. And here is the XOR. So for the XOR, the input is 1, so it's exclusive OR gate. So whatever you have here, whatever binary level, maybe 0 or 1, the reverse is what is happening here. And this is the function block equivalent of the XOR, where you have just 1 in this block. And here you have so for the NOT, you have one input for the NOT gate, so one input going into one output. So whatever the input has as its own binary level, maybe 1 or 0, the opposite is what the output would have. That's why this NOT sign is here, and this is the function block diagram equivalent of the NOT gate. For the XOR, this is the symbol of the logic of the XOR. There are two inputs and one output at least. So in this case, it's only when one of the inputs has a binary level of 1 that the output would have a binary level of 1. So here, this is the function block equivalent of the XOR gate, which is showing a sign of equal to 1. So we can see a difference from the OR gate and the XOR. For the OR, it is greater than or equal to 1. So for the OR gate, there are instances whereby the 2 can have a binary level of 1 and the output would still have a binary level of 1. But for the XOR, it's only when either of them has a binary level of 1 that the output will have a binary level of 1. So at other instances, the output here will have a binary level of 0. So for the ladder logic and its convention, looking at it in depth, so the ladder logic looks like a normal ladder where you have the rail and the run. So for the ladder logic, on the run is where circuit components are being shown, and the left and right rail are referred to as the power rail, and power always flows from the left to the right rail. So this diagram here shows how power flows on your ladder diagram. It flows from left to right, top to bottom, 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 until the final run, which is the end run. So that is the diagram of your ladder. Now, for understanding of the ladder logic, supposing we have a circuit like this, where you have a bulb as the output device, a switch in this case as the input device, which is normally opened, then the cell where the power is coming from, the battery in this case, so it has the negative and the positive terminal. So power flows from left to right, and in this case, to show this circuit on a ladder diagram, this is the equivalent. The input device is always shown to the left, while the output is shown to the right. So in this case, since the switch here is shown as opened, that is why these two bars has no line crossing in between, showing that this is an open contact. But in case where, for instance, if this switch here is shown as normally closed, then this line here will be drawn crossing in between these two to show that this is a normally closed contact. But the ladder logic itself has its own convention. There are about 6 conventions to writing a proper ladder logic diagram. Number 1 is the vertical lines, which is what you have on the left and on the right, represent what is known as the power rail, and power flows from left to right, like we already said. Now, on each run of your ladder, each run must define at least one operation in the control process. So each run on the ladder must define one operation in the control process of your PLC. And also the ladder is read from left to right, top to bottom, like we already said. So the reading of a ladder from the first run going left to right, top to bottom to the last run is what is called a cycle in ladder logic programming. Now every run starts with an input component and every run ends with an output component. Another thing is electrical devices, they are shown in their normal state. So if a switch is normally open, it's shown as normally open on the ladder, or if a sensor is normally energized, so such a sensor is clearly shown as such on the ladder diagram. Another thing that has to be noted here is that a particular device can appear repeatedly on several runs of the ladder depending on what control operation is being done on such runs. And one particular thing about ladder diagram is that every component, be it your input or your output components, they are being identified by their addresses. Now in ladder diagram, the address always have an alphabet and a number. So it's a kind of alphanumeric method of writing program. So there's an alphabet and there is a number. Now the alphabet depends on the manufacturer of that PLC. For instance, Mitsubishi uses X for input components and Y for output components, whereas Siemens uses I for input components and Q for output components. So the address and notation depends on the PLC manufacturer, which needs to be known by the user. So before we go on to looking at programming PLC using the FX training software, I just want to show some symbols. Now, like I already said, this symbol here shows your normally opened contact, where this one shows your normally closed contact. For your outputs, you have this parenthesis, your normal bracket, showing this is an output. Then in some cases you might have an instructed output, so that one is being showed using a square bracket. So this is an instructed output, where this one is a normal output. Then also there are some instances whereby you want to know momentarily when a particular component changes state from 0 to 1 or from 1 to 0. So in that case, you'll be using a rising edge detection with this symbol, with this arrow going upward. This shows that you only want to know when this component changes states from binary 0 to binary 1. So this is a rising edge detection. However, if you want to know when such a component changes states from 1 to 0, so that is shown with this arrow pointing downwards, which is a falling edge detection. So because in this video we'll be looking at the Mitsubishi PLC, so we'll be using the Mitsubishi convention. So X are for input devices, Y are for output devices, and your letter M are for relays. Letter T is for timer, and letter C is for counter. Now for the timer and counter, there's always a K number. Now this K number here for timer, whatever value is being given to the K is divided by 100. So if you have K 100, that is 1 second. So that is, if you have T 1 K 100, that is, you're saying that after 1 second, this contact, which is T1, would be energized. So for timer, whatever K number that is there is divided by 100 to get the number of seconds for that timer to be energized. Now for the counter, the K number for the counter is the number of time the counter will count before that counter gets energized. So the K number for counter is the number of counts that the counter needs to go through before such a counter is being energized. So we'll be using the FX trainer now to do some simulation to understand the concept of the PLC better. Now this is the interface of the FX trainer once you have it installed on your system. So it's a Mitsubishi simulation software for PLC. Now here we have, on this operation panel, we have input and output devices. And how do we know that? By the alphabet. Here you have Y10, Y11 and Y12. Because the letter Y is preceding these numbers, this shows that these three devices are output devices. If we come down here where you have the operation switches, we have X10, X11, X12, X13, X14, X15. Because of the alphabet X, with that we know that all of this are input devices. So if you look at this column here where you have the run, input X, output Y, these are the terminals where these input and output devices are connected on a PLC. This is just showing the model of the PLC. So the PLC in this case has input from 0 to 27 and output from 0 to 27. So X10 is on this in X10, 11 and so on in that manner. So the first thing that I want to show is some basics of the PLC operation. So to write any program, you need to first of all click edit ladder, because we are using ladder logic in this case. So here is the ladder itself. So the ladder programming is done here, and after that it is being converted using this convert tab, then write to PLC tab here. So it begins to operate just like you would when you are working with a live PLC. So for instance, F5 here is a normally open contact, F6 is a open contact branch, the SF5 here is a normally closed. So you can just pick this normally opened contact. Now it has to have an address. So here we have X10, X11, X12, X13, X14, X15. So I have to address this contact to any of this. So if I'm addressing it to X10, so I'm saying that, okay, you can see here that we have X10 on this first run. So X10 is an input device. What do I want to happen? Because every run must define a control operation. So you have an input already, there has to be an output on this run. So the output that we have here are just three: Y10, Y11, Y12. So if I put Y12 here for an output device, this is an output device, not an instructed output, in this case just a normal output. So that's Y10, and I click enter. So here we can see X10, Y10. So if I convert this and write to PLC, what will happen is that Y10 will be taking input from X10. So convert, write to PLC. So in this case, we see that this is where we have our X10, and X10 is a push button because this is PB, so push button. If I hold this down, we can see now that my Y10 is being light up. So, and if I release it, it goes off because this is a push button. So I need to press it for the Y10 to be light up and release it so that it goes off. Now if we look at the area, this area here, we can see that Y10 and X10 has these blue colors. Now these blue colors is showing that these devices are energized at this time, that they are energized. If I release this push button, you can see that the blue colors are gone, showing that they are no longer energized. So a contact can be opened or closed and be energized or de-energized. So there are different things. The contact can be opened and energized, and at the same time it can be opened and de-energized. At this time, X10 is opened and it is de-energized. But if I press this button here, X10 is opened but is energized. So for a open contact, current will only flow through when it is energized. That is for a open contact. But for a closed contact, current will flow even when it is not energized. So let's try and do that now. Let me edit the ladder and make X10 a normally closed contact. Now I'm putting X10 as normally closed contact. You can see now that X10 is closed. When I convert and I write to PLC, I click OK. Now we can see that once the PLC is in run mode, the lamp is on, the Y10 is on. Why is that? Because once a contact is normally closed, current will flow, and because current is flowing, it will show as energized. So this is where the NOT logic comes in. The contact is closed, the lamp is on. If I press this button now, we can see that the lamp is off. So this is a NOT logic now. This is a NOT logic. So if I release this again, the contact is closed, the lamp is on. I press the button and the button is now pressed. And I press the button now, the lamp is off. So this is a NOT logic. So let's show the OR. In this case, we have to use two. Let me edit this. We have to use two inputs because we want to show the AND logic. So let me change this to a normally opened contact, and I want to change this to a switch. So that's X14, or let me use X15. They are both switches. So that's X15, and also I want to put the push button X11. X11. So when I write this and Now for Y10 to be energized, X15 and X11 has to be energized, and if you look at it, they are both opened contact in this case. So for current to flow, both of them has to be energized. So X15, this is X15 and it's a switch. So I put a switch on, the switch is on now, we can see that it is energized. So the current is flowing from here and is stopping here because X11 is opened and it is not energized. For X11 to be energized and for the AND logic to actually work, I need to press this push button X11. So when X11 is pressed, we can see that X11 here is energized, showing this blue color, and Y10 is energized, showing this blue color here, and we can see that the lamp Y10 is on. So that is an AND logic because the two contacts, which is the X15 and X11, has to be energized. They have to have a binary of 1 for the outputs to have a binary of 1. So that is the AND logic. So let's look at the OR logic. Let me edit this ladder and let me delete X11. Let me delete X11. Delete this line. So we have X15 and we have Y10 as output. Then I want an OR arrangement, which is X11 in this case. So I'll write to PLC. So if we look at this, we can see that we have X15 here and X11 here. Now from the convention of ladder, we know that power flows from left to right. Now to get to Y10, power can flow directly from this line through X15 to Y10, or power can flow from X11 and here to Y10. So if I put switch X15 on, then Y10 is energized. If I put this switch off, Y10 is de-energized, and I press PB2, which is X11, Y10 is equally energized. So this is the OR logic, whereby either of the inputs with a binary of 1 will cause the output to have a binary of 1, and even when the two input has the binary of 1, the output will still have a binary of 1. So if I want to show that, I put on the switch and also press the push button. We can see that both X15 and X11 are energized and power is equally flowing to Y10. Y10 is energized because of these blue colors, and we can see here that the lamp is on. So another thing I want to show here again is what we call precedence. Precedence in the sense that if you want a particular contact to control the operation of a particular run, that contact is shown on the run to have precedence over the inputs that you would want such a contact to have precedence over. For instance, X15, X11, if I want X12 here to have precedence over these two, then what I'll do here is to edit this ladder, then put X12 here. X12. So, and let me convert this and write to PLC. Click OK. Now, from here, X12 is having precedence over X15 and X11. If I put on the switch here, we can see that though X15 is energized, Y10 is not energized because X12 is taking precedence. So, regardless of the state of X15 or X11, X12 has to be energized for Y10 to be energized. So in this case, I need to press the push button here, that's X12, before Y10 can be energized. And when I release it, though X15 is energized, Y10 is not energized. And the same goes for X11. If I press the push button X11, you can see here that Y10 is not energized unless I press the X12. So for me to show that, let me just edit this and convert my X11 to a normally closed contact because they are both push buttons. So let me write to PLC. Now in this case, we can see that X11 is a normally closed contact. So based on that, once the PLC is in run mode, that contact is energized. So current is flowing from this left rail through X11 to this point, but it cannot go through to Y10 because X12 is taking precedence in this case. So until I press this button here before Y10 can be energized. So that is precedence. Now another thing is what we call latching. Now latching is whereby you want an output to stay energized even when the input that is controlling the operation of that output is already de-energized. For instance, in case of push buttons, once you press the push button and you release it, the contact goes back opened. However, if you want the output that is being tagged to the push button, you want the output to remain energized even when the push button is opened, then you need to latch such arrangement on the ladder. And the method to latch is this. For instance, I want to latch this Y10. Let me edit this. So if you are latching this, you can change this to Y10 and it's normally opened. So that's normally opened. Let me remove X12. What's X12? And this one to a push button, which is X10. And write to PLC. So here, this is the latching operation. This is one way to latch. Now the push button X10 is a push button. When I press it, the contact goes back opened. But because here I've put the Y10, which is the output here, and I've latched it as an OR branch to this run. So once Y10 is energized here, Y10 here is showing here as a contact, as an input contact. So at that time, it will equally be energized, and Y10 will stay energized. If I press here, now we can see that X10 gone from being energized to being de-energized. However, my Y10 stays energized. It's because of this arrangement, making Y10 another contact with an OR branch to this run. So once Y10 is energized, this contact equally is energized, and Y10 remains energized because current is flowing from the left rail through here to this point to Y10. However, we can see that there's no way to put off Y10 in this case because there's no precedence here. So this is where precedence is required. There has to be a stop button here so that Y10 can be put out. So in that case, you will need maybe a push button that will be normally closed in its normal state so that current can flow. X12. Because if X12 is not shown as normally closed, there is no way current will flow at the instance of Y10 being energized. So once X10 is pressed now, we can see that Y10 is energized. Now because X12 is shown as normally closed, so current is flowing from Y10 here through X12 to Y10 output, and it stays energized. Now because X12 is taking precedence in this case, so X12 is the stop button. So once I push in X12 here, we can see that the whole system goes out. Y10 is off, and we can see that X12 is energized. X12 is energized because it's a normally closed contact, so it's allowing current to flow. Once you press it, you can see that it's opened, it's no longer energized. So it was that at that instance the Y10 was able to be put out. If you start the process again, push button X10, you can see that Y10 is energized. Once I press X12, so that momentary de-energizing of X12 is what took out Y10. So this is one way to latch. There's another way to latch, which is the instructed output method of latching. So I will just edit this. In this case, you don't need to use this arrangement of latching. Just cut this line out. Cut this line. And also I'll be removing X12. Just join this line together. I'll be taking out this. So in this case, I also use an instructed output. So I'll be using the set Y10. So what set Y10 is saying is that once X10 is pressed, Y10 is set to be on. So let's convert that before we show how you can put it off. So once X10 is pressed now, Y10 will stay energized because I've used an instructed output in this case that set Y10. So once that is pressed, you can see that the X10 has gone to being de-energized, yet Y10 is energized and the lamp here is on because this output here is an instructed output set Y10. So if we push X10 repeatedly, nothing is going to happen. because once you set an output, then the output, for that output to be put off, the output needs to be reset. So in this case, let me edit again, then I'll use another run to reset this Y10 to put it off once it has been set on. So I'll be using X13 in this case, which is a push button again. X13, this is X13, and I'll be using the instructed output. That will now be RST Y10, that is reset Y10. So convert this and write to PLC. So this arrangement is the second method of latching. We can see that once the PLC is in run mode, by default the reset is energized because Y10 is not energized. That's why it's the reset that is energized. You can see the blue color on the reset. So once I press X10 now, you can see that Y10 is set on, though my push button X10 is already opened, but this circuit has been latched using this instructed output. So with the set Y10, it stays on. So the only way to put it off now is this reset line that I've added here using X13. So X13 is the stop switch, while X10 is the start switch. So if I push this button, which is X13, you can see that Y10 has gone off. And if I push X10 again, it goes on. X13 it goes off. So this is the second way to latch. So the next thing I want to show is the timer and counter. So let me edit this and cut this and change this to a normal output. So let's use Y11 in this case. So Y11 is the output in this case. X10 is the push button. So let's change this to a switch. Change this to X14, which is a switch. So what will happen in this case is once I put on this switch, Y11 would be on. However, I want Y11 to go off after 5 seconds. So if I want to go off after 5 seconds, that means I need a timer that would count for 5 seconds, then put off Y11. So in this case, I'll be putting, let me delete this line, don't need this line. So on this run now, I will have the timer to take precedence as a close contact. So that will be T1. However, this T1 needs to count so that it will either go energized or de-energized. So I'll be latching it to the output here, not to the input end, because I actually want the timer to start counting when the output is energized. So I will put in the timer here as, so that will be T1 K500. So T1 K500, that means after 5 seconds, because whatever K number you are giving to a timer is being divided by 100. So 500 divided by 100 will give you 5. So that's 5 seconds. So let me just join this line here. So you can see now. So once this output is energized, this timer begins to count. Now this timer here, this T1, which is the timer, is shown here as normally closed. Why is this? Because I want the current to flow once my switch X14 is being energized. So that once my switch here is energized, current will flow because T1 is normally closed and Y11 will be energized. and this timer will start to count. However, when this timer counts for 5 seconds, then this T1 here will change state, will go from being energized to de-energized, so which will open this circuit and cause this timer to go off. However, let's see how this would work in practice. So you can see here that we have T1 K500 and we have 0 here. This blue colored 0 here is the counter that will start to count, and we have T1 here as energized because it is a normally closed contact, which will allow current to flow. But however, once this one counts to 500 here, which is equivalent to 5 seconds, this one will go de-energized. So at that point, this Y11 would go off. However, this will turn out to be a kind of flash light arrangement. You can see this one is counting. So once it counts to 500, the lamp will go off and go on again. Why it will go on again is because X14 is a switch. So you can see here that X14 stays energized. So whatever happens to T1 in terms of change of state will only be momentary, which will cause this Y11 here to just be flashing, just flash and go back on. So here is still counting up until 500, which is 5 seconds. So once it gets to 5 seconds, we'll see that we can see that one went off and went on again. So it was at that time this T1 went to change of state, so it goes to de-energize and Y11 will go off. But because X14 is a switch and it stays energized, that's why the lamp came back on. But to prevent that, we would make some corrections, which I will show in a bit. I just want this one to count again to 500 so you can see the lamp go off and go on again. So let me edit this and change this to a push button, in this case X10, and I'll latch Y11 to it so that it will actually go off. So Y11 convert and write to PLC. So what will happen here is this: once I press the push button X10, which is this one goes to energize, then current will flow to Y11, and because Y11 has been latched here, it will stay on. However, once the timer counts to 500, which is 5 seconds, then the whole system will go off. So let me just put this. We can see that the lamp is on and this one is counting. So after 5 seconds, which is K500, it will go off this time. So we can see that once K500 has been reached, the lamp went out because the contact here, K10, is a push button which has gone de-energized after the button has been released. So although the P1 is a normally closed contact, energized, waiting for current to flow, no current is flowing, unlike the other time when we have it as a switch, which this one was X14. So that's why the other time it was just flashing, but now that's gone off. So put it on again, X10 has to be pressed again, so you can see. So that is for the timing or using a timer. The next one I want to show now is the counter. Let me edit this. So the counter works similar to the timer, but in this case I want to make an arrangement whereby I want to count 5 times when Y11 as common. So after 5 times Y11 as common, I want Y12 to be turned on. So after Y11 as common for 5 times, then Y12 would come on. So in that case, I would need a timer to count the number of times Y11 has come up, and after then Y12 should come on. So let me show that by it. I'll change this one from T1 to C1. So that's a counter. So this one will change from 500 to 5. So just 5 counts of that. So I will not be latching this anymore because actually no number of time. Let me just remove this line. And here again I will have to remove T1 because T1 is no longer in the picture. So then my C1 will now be the input device for my Y12, so that we'll understand the concept of counting. So Y12. Let me convert this and write to PLC. So what will happen here is this. I'll be pressing push button X10. 1, 2, 3, 4, 5. Y11 will flash 5 times, and counter C1K5 will count 5 times here. After the 5 counts of this T1, then the contact C1 here will be energized, which will put on Y12. So that's just the operation here. So I'll press this. When I pressed once, you can see K1. Press second time, you can see again 2. Press again 3. Press again 4. Press again 5. Once one is 5, you can see that Y12 came on, because at the time K is on 5, T1 is energized here, and we can see that Y12 is turned on. But one thing about using counter is that whenever you use a counter, there has to be a form of reset for that counter, else the K number will stay at the set point. In this case it's 5. You can see that 5 is here. So to make this counter go back to 0, we have to reset this counter C1 using any of the input devices here. So in this case, let me use X12 to reset this counter. So let me edit this and put here X12, then instructed output, in this case RST C1. So reset C1 using X12. So let me convert that and write that to PLC. So I'll press X10 5 times again. 1, 2, 3, 4, 5. We can see now Y12 is energized, C1 is energized. Now to reset my C1, you can see here is 5. Reset it to 0. Then I need to press X12 because X12 here is used to reset RST C1 and instructed output. Once I press this, so we can see now that C1 has gone to 0. So X12 has been used to reset C1. So whenever you're using a counter, you have to reset it. There has to be a run whereby that counter will be reset. So the next thing I want to show are relays. Relays in Mitsubishi is alphabet M. So relay can be from 0 to whatever number, maybe from 0 to 999. Can be M0, M1, M2, M3, M4, and so on. However, there's a special relay with Mitsubishi that is being connected directly to the run button of your PLC, and that is your M8000. Now M8000 is a special relay that is connected directly to the run button of your PLC. So what that means is, if you are using M8000 as an input to a particular output, once your PLC is in run mode, that output is energized and it stays energized. For instance, if I edit this and change this to M8000, M8000, let me remove this counter, cancel this line, or let me just delete this whole line. It's this line as well. So let me change this to my M8000, M8000 Y12, and let me delete this line as well. Let me delete this line, I don't need it for now. To convert. So once I write to PLC, the PLC goes to run mode, and we'll see that Y12 will stay energized because M8000 is connected directly to the PLC run button. So we can see once PLC is in run mode, without pressing any button, Y12 is energized because M8000 is a special relay that is connected directly to the run button of your PLC. So this is M8000. Let's look at another kind of relay. Now, why relays are important is that timer, counters, or sensors which are being shown as input devices cannot in all cases output the current or the voltage that the output device would need to function. So that's why relays are always used. So in place of putting timer or counter directly to start an output device, there's always a need to use a relay. So let's just show an arrangement of a relay. In this case, let me edit this ladder. So let me say I want to use X10 to, let me just edit this, change this one to X10. So X10, but I will not use X10 directly to put on Y12. So I'll use X10 to output X10 into a relay M1, then using M1 now as the input to Y12. So convert this and write to PLC. So here is the relay arrangement. Now X10 will output into relay M1. So relay M1 now would now be the input contact into Y12. So you can see that it's going off. Why it's going off is because my X10 is a push button, so I need to let me just latch my M1 here so that Y12 can stay energized. M1. Let me put a precedence here so that I can put off this. Let me put a precedence, in this case X11 as precedence. So the X11 will be the stop button. From here. This should be, let me edit this. This should be a normally closed contact. So current will flow. And I will cut this one from here. To latch it here. So this is M1. Create a line here. So M1. So that's it. Right to PLC. So X11 is the stop button here because it's taking precedence over X10, M1, which is the latch of this relay, and is M1 that is putting on Y12. So once I press this, you can see here that Y12 remains on. Now because X11 is normally closed, allowing current to flow, X10 is the push button. It goes to de-energized after I release it. However, because I've latched M1, M1 stays energized, and M1 is the contact that is used to set up Y12. So that's why Y12 stays energized. So when I push in X11 now, the whole system goes off. And to start it again, to press X10. So X11 is the stop button, on, off. So the next thing I want to show is the rising and falling edge detection. So for instance, I want this relay M1 to only be energized when my push button goes from 0 to 1. Then I'll be changing this, edit ladder, changing this to a rising edge detection. So that is this P sign. So you can see the arrow going up, convert. So in this case now, once I press my push button, M1 will be energized when it will actually see the workings of this. Let me edit this and remove the latch. Edit, remove this latch here. Let me cut this latch off so that we can see the operation of the rising edge. Right to PLC. So M1 would only be energized when this push button goes from 0 to 1 because it's a rising edge. So we can see if I hold this down here, we can see that M1 is no longer energized, though I'm holding down the push button, because I've used a rising edge detection in this case. So it's only when X10 goes from 0 to 1 that M1 will be energized. However, I press the button down, though the button is in contact. However, because of the rising edge detection in the ladder, M1 would not be energized. So that is the rising edge in this case. So for falling edge is from 0 to 1. So let me equally edit this, edit the ladder, and use this as a switch so that we can even understand it in a much better way. X14. So convert and write to PLC. If you look at it, this is X14, is a switch. If I put it to on, is on, however, is no longer energized here because it's a rising edge. And if I put it off, it goes off. However, it's only momentary when it goes from off to on that is only being energized because it is a rising edge section. So you can use rising edge or falling edge to actually make a switch work as a push button and use it. Let me just change this again to a falling edge so that it's only when the switch is going from on to off that and see M1 flashing the energized symbol. So if you look at X14 now, if I put it on and see that nothing happened, there is no blue color showing energized. But however, if I put it off, you can see that momentary blue flash showing that it is a falling edge detection. So that's for falling edge and rising edge. So from now we'll go on to actually looking at some industrial automation use cases, having gone through the basics.
We have here a diagram showing a system industrial operation
Use case in FX Trainer. So you have here a diagram showing a system industrial operation where you are already told that Y5 is a supply command, X5 is starting point, and that is an input device. You have Y5 for conveyor forward. Now you have X0, X1, X2 for upper, middle, and lower. Then you have X4, which is another input device here. So you need to go through the control objective, because for every PLC you might want to program, there must be a control objective. Now the control objective here is to sort 3 different sized parts carried on a conveyor. So from this objective now, we're saying that this supply arm will supply parts of 3 different sizes, and which would be sorted based on these upper, middle, and lower limits input devices. So that is what the control objective is. So what are the control specifications? Now I read here, the following operations should be performed in this unit. Study the required specification and then create the program and confirm the operation. So number 1 says when PB1 X10 on the control panel is pressed, supply command Y5 for the robot is turned on. When PB X10 is released, supply command Y5 is turned off. So what it's saying is that for the first run, once X10 is pressed, then supply command, which is this arm, Y5 should be energized and a part should be supplied on this conveyor. So that's the first instruction. However, we need to note something here, that we have X5, which is starting point. Now this X5, and when you look at the PLC terminals here, we can see that X5 is energized, showing that this red light here, showing that this X5 is energized. Now this X5 is a switch or a sensor sensing the presence of this arm at this point, which means whatever X10 is doing has to be subject to X5, which means X5 has to take precedence over X10. So to do that, let's just edit this ladder. Let me delete off this line, delete this line, and change this to to normally open contact for X10. Normally open contact for X10. Then I'll change this one to normally close contact. To normally open contact, sorry. So that it's only when it is energized, that means the arm is there, that it's going to be energized. So X5. So into M1. So M1 will now be my input device for my Wi-Fi, because I can't actually start my Wi-Fi with my push button. So that's why I'm using a relay with it. So this is my Wi-Fi. So convert that and write to PLC. So we're going to look at the first line of the specification. If we have been able to answer that correctly, you can see here it says when PB1 X10 on the operation panel is pressed, supply command Wi-Fi for the robot arm is turned on, and when PB1 X10 is released, supply command Wi-Fi is turned off. Now you can see here that X5 is already energized. This is stating that, and is a normally open contact, this is stating that the robot arm is already at the starting point. So which means it's safe now to push the push button X10. So you can see that pushing the push button X10, you can see that a part has been supplied on the conveyor. So, and we have used a relay here because we cannot use our push button to start this arm. So that's why a relay has been used in this case. So let's move on to the next. Number 2 states when operation starts, X14 on the operation panel is turned on, conveyor forward Y3 is on, and when X14 on the operation panel turned off, conveyor forward Y3 is off. So that's the next one. Switch X14 controls the conveyor Y3. So edit ladder, I've already put my switch as normally open because I had to switch the switch to work. Then I'll put that also into a relay M2. So my relay M2 now put on my conveyor. So that's Y3. So we don't need to latch in this case because the input is a switch, so it stays energized. So let me convert and write to PLC. Okay, so let's check X14. So X14, the conveyor should start moving forward. Now you can see here, you can see this cog or whatever it is rotating forward here also. That means conveyor is already moving. And also if I push in X10, we'll see that the part will move because the conveyor is already in operation. So we can see that. So that is that. And again, let's go on. Let's see the third requirement. Now it says large, medium or small parts carried on the conveyor are sorted by the inputs of sensors X0, X1, X2. So which means these sensors X0, 1, 2 would sort the size of the part based on their inputs. So X0 is for upper limit, which is large, which corresponds to Y10. The middle or the medium, X1, which corresponds to Y11, and the small, which is X2, which corresponds to Y12. So number 4 says a lamp is lit immediately after sensor this X0, 1, 2 sort the size. A lamp is lit immediately after this sort the size, then it is extinguished when the part has passed X4. So if we listen to this specification very well, we'll notice a falling edge requirement here. If you look at number 4, it says a lamp is lit immediately these sensors senses the size, and that lamp is being put off once the part passed X4. So once the path pass x4 is when the lamp that has been lit based on the input of x0, x1 and x2 to be put out. So that's a falling edge, because at that point x4 will go from 1 to 0. So but let's walk around it. For large, medium and small corresponds to y10, y11, y12. So, and one other thing we have to look at here critically is that we can see that all these sensors x0, x1, x2, they are inline, which means they all will sense the path at the same time, and the size of the path will determine which of these sensors will be energized at that time. So based on that, it is best and reduce having several runs to put all of these sensors on the same run, and the corresponding lamp would be energized based on the size of the part. So let's just edit this ladder. So here, so I'll be using 3 runs, one for the upper, another one for middle, another one for medium. So for the upper, so I have here x0, which will be normally opened. So it's only a part of upper limit that will close this x0. However, I will put x1 and x2 as normally closed, so that only when the part is of upper limit that power will flow on this run, since I know that all the sensors are inline and they will sense the part at the same time. So here we'll be having x1, and again we'll have x2, which would output into another relay. Let me call that M3. So my M3 now will now put on my Y10, because Y10 is for the upper limit, Y10. But again, this is M3 input, then output is set Y10. Why I'm using set is this, because when we look at what we have here, it says a lamp is lit immediately after the sensor this x0, x1, x2 sort the size. So then is extinguished when the part passed sensor x4. So the lamp comes on and it stays on until it passes x4. So that is a kind of latching in a way, so that once it has sensed the part, the lamp will stay on until it crosses x4. So that's why I'm using instructed output here, so that once on this run x0 is energized based on the size of the part to be an upper limit part, and I've closed x1 and x2, current will flow, M3 will be energized, and M3 would set Y10 to be on. And once Y10 is set on, it will stay on until x4 puts it off. So let's just copy these 2 lines for both middle and lower limit. So I'll close this. Close upper. I will open medium x1, then close small x2, then output into M4, and I'll use M4 to set Y11, M4, then set Y11. Then I'll repeat the same thing for small. So for the small now, I would copy this line. Let me just copy this one, paste here, x0, then x1 will be normally closed, and I'll leave x2 to be open. So it's when the part in this case is a small sized part would allow current to flow through this run. So that will go into M5 as the relay in this case, and I've used M5 to set Y12. M5 set Y12. So I've done the upper using this run. So leaving X0 opened, closing X1 and X2, since all the sensors will sense the part at the same time. So if it's the upper limit part, current will flow here. Here I'm closed X0, open X1, close X2. So if it's a medium sized part, current will flow on this run. And on this run, lastly, I've closed X0, closed X1, then opened X2, so that if a small size part, current will flow on this run. So, and the instruction says the lamp, whichever one it is, Y11, Y10, Y12, will be extinguished once the part passes X4. So in this case, X4 will be the reset for all the lamps. So that is what it is saying. So X4, then since I've used an instructed output, then I'll be using reset, in this case RST Y10, and I'll just be latching all the other outputs, RST Y11, then RST Y12. So let me just link all of this here. With this line, all of this. Just okay. All right, so I'll just convert this. Let me see how that would work. Okay, something wrong here. Let me delete this line. Let me insert a line here. Put my RST Y12, showing that this. So what will happen is X4 will reset Y10, Y11, Y12, depending on which of them is energized based on the size of the part. So let me convert this and write to PLC. So let me just run through the runs. Number one, what will happen here is once I press X10 and Y5 is energized, M1 will be energized, and M1 would energize my Y5. So my arm would supply a part. Switch X14 here, once I put it on, to energize and energize M2. So M2 in turn will energize Y3. So this conveyor is Y3 conveyor forward. So conveyor moves forward. Now for the sizes, like I said, since all the sensors X0, X1, X2 are in line, they will all sense the size of the part at the same time. So they can be put on the same run using the NOT logic. So here is for the upper limit, leaving X0 opened, closing X1, X2. It's only when the part is in upper limit size that this run will be energized, and M3 will be energized, and M3 will now set Y10 on. So this lamp Y10 will be on at that time. However, if the part is a medium sized part, so this is the run for that, close X0, open X1, close X2. So it's only when the part is a medium sized part that X1 will be energized and current will flow in this run. M4 will be energized, and M4 will set Y11 on. Then if the size is a small sized part, here is the run. X0, X1 normally closed, open X2. So if the part size is a small size, X2 will be energized, and when X2 is energized, M5, which is the relay in this case, will be energized, and M5 would set Y12 on. And since the instruction says all these lamps should be put out once the part passes X4, so I'm using X4 to reset all the output Y10, Y11, Y12. So I press X10 now, and see part is supplied. Part is supplied, and I put on the switch. Conveyor moves forward. We can see that in this case that's and it goes like that. So something is not working right here. Let's see. The lamps are not staying on. Upper limit. So we can see all the three lamps came on. Okay. So let's see why this large and medium lamp is not coming on. Let me edit my ladder and go to the run where I have my upper and medium. Okay, so here is the problem. You can see here what we have done here is to open X0 and close X1, X2. So this is wrong because at the time the part is being sensed, this one will go on to de-energized. So that is why the lamp is not coming on. All these ones should be left opened. Since the sensors are inline, they all will sense the part at the same time, so they will go energized if it's an upper limit. So let me just open all of this so that once the part is upper limit, they all will get energized. And the same will be done for this one. If it's medium, both the medium and the small will be energized so that the current can flow. So that's just the correction that is needed there. So what we have done is to change this one from being normally closed to normally opened. Since all these sensors, they are inline, they will see the part at the same time and sense it. So if it's upper limit, all the three will go energized, and here all of them will go energized, so M3 can be energized. However, if it's a medium sized part, only X2 and X1 will sense it. So that's why X1 and X2 are left as normally open here, while X0 is normally closed. So that once this two senses it, then M4 will be energized for medium. And when only X2 can sense it, that means it's a small sized part. So all the lamps should work now and everything should work fine. So put conveyor on. So we see when all the three sensed it, the lamp L1 came on. And if another part is supplied for medium, let's see. For medium, we'll see that the medium lamp would equally come on. So that is for this one. So we're going to look at another example. So you can see that again. So let me So let's look at this one. Okay, so here is another industrial operation. You have the arm, you have Y7 for the supply command, X5 for the starting point, which means this arm is at this position. Then X0 is a sensor here. Then the upper conveyor here, Y0 is forward, Y1 is reverse, X1 is this sensor here. Middle conveyor, Y2 is forward, Y3 is reverse, X2 is here, this sensor here. Lower conveyor, Y4 is forward, Y5 is reverse. So let's look at what is being requested here. It says the objective here is to operate the conveyor according to the sensor data. The following operations, okay, so let's look at it. So when PB1 X20 on the operation panel is pressed, apply command Y7 for the robot arm is turned on if the robot is at the starting point X5. And when PB1 X20 is released, apply command Y7 is latched until the robot arm returns to the starting point. Now this needs to be looked at critically. When X20 is pressed, Y7 is on, is turned on. That's if X5 is at the start point, and X20 is released, Y7 is latched until the robot arm returns to Y5. So let's do that. So we have X20, which is a push button. Then, sorry, this should be normally open for X5. So that should output into a relay M1, and relay M1 should output into Y7. So let's see if that is correct. So X20, so we can see that one is working correctly. So the second line says when sensor X0 detects a part, the upper conveyor forward Y0 is set on. When sensor X1 detects a part, the middle conveyor Y2 is set on, and upper conveyor forward Y0 stops. So we can see that once X0 senses the part, Y0 is set on, and when X1 senses the part, Y0 is stopped. So this is a set and reset kind of approach. So let's edit ladder. So when X0 senses the part, Y0 should start. So X0 into M2, then M2 to set Y0, set Y0, set Y0, set Y0. So M2 sets Y0, then X1 sets X1 into M3, and M3 sets Y2, M3 sets Y2, sets Y2, and we are told that X1 should stop Y0. So I'll put the reset of Y0 with M3, which is the relay that is started with X1. So let me insert a line here. So So let me put my reset, my RSTY0 here, and join these two together. So let's look at that. So what will happen here is that once X1 senses the path, it outputs into relay M3. M3 will set Y2, which is this middle conveyor, to move forward, and once this one is moving forward, then Y0 should be stopped. Okay, so I could have put this reset here. Sorry, let me edit this. Let me put this where it should be appropriately. Let me delete this. Sorry, let me cut this off. Or let me delete this line. So let me insert a line here and put my reset Y0 here. So RSTY0, RSTY0, RSTY0. Okay, that's position error. RSTY0. So let me just add this to this line. So convert, then write to PLC. So once X1 is energized, Y0 will go off. So let's just look at that. X20. So once the path is sensed, it moves forward. Once this one senses it, you can see that Y0 has stopped. So I think it's the same for so when X2 senses the path, the lower conveyor forward Y4 is set on and Y2 is set off. When X3 detects the path, the lower conveyor Y4 stops. When sensor X3 is set on, supply command Y7 for the robot is turned. Okay, so let's just take it in bits now. So we'll repeat this edit ladder. So we are on X1, which is this. So when X1 senses the path, okay, Y0 is stop. When X2 detects the path, lower conveyor Y4 should be set on. So X2, when X2 is energized, Y4, so this should output into M4. So M4 should, okay, let me insert a line here so that I can use that to stop Y2. So reset Y2, RST Y2, and join this line together so that current can flow there. So M4 now, M4 will now set, M4 will set Y4. M4 will set Y4. Set Y4. So set Y4. Then when X3 detects the path, then Y4 should stop. So X3 should go into relay M5, then put a line here to reset my Y4. Reset Y4, RST Y4. So join this to this, and M4. So when sensor X3 detects the path, lower conveyor Y4 should stop, and when X3 is set on, supply command Y7 for the robot arm is turned on. Okay, so this one is not here. Let me delete this line. Okay, let me first of all convert this and let's see all the conveyor operations before we now go to this objective 6. So once X20 is pressed, so this part should go from here up until X3. This one is stopped. This one is stopped. So all of this has been implemented, and what is left now is that this number 6 is saying that when X3 is on, supply command Y7 for the robot is turned on and a new part is supplied if the robot is at the start point X5. So what is happening is that once a part has got into X3, we don't need to press X20 again for a new part to be supplied, as I'm doing now. X3 should start the whole process again. That is what this line 6 is saying. And when sensor X3 is on, supply command Y7 for the robot is turned on and a new part is supplied, provided the robot arm is at starting point X5. So what is going to happen is that since my M5 is the relay attached to X3, so I only take Y5. Let me edit this line and insert a new line here. So all I need to do is to latch M5 here, and the question says provided the robot arm is at the starting point X5. So X5 will take precedence. That is what it's saying there. So this one will be M5, and I will just put that as an OR logic into this. So write to PLC. So once a part has gotten to this X3, a new part will be supplied without pressing the X20 again. So that is what is going to happen. So we'll see now. So here is another use case where you have the robot arm by command Y0, X0 indicating means that it's 3 sensors here, X1 are inline, means the 3 sensors will sense the part in this conveyor at the same time. Y1 is for conveyor move forward, Y2 here is conveyor to move forward. Then Y5 is wing, Y is here, X5 is a sensor here. Let's see what's been requested of us in. So number 1 says when X24 operation panel turned on, conveyor moves forward. When X24 is done, the conveyor stops. So in this case, that will be for the 2 conveyors. That means X24 controls both the Y1 and Y2. So the second case says when X20 vision panel is pressed, so Y0 for the arm is on, 0 is turned on. That's in. So this says total supplies lab. That's the conveyor. So here we just yes. I1, add, which is just add some. That's it. So the next thing is for white. Here we just here 20 and 0 we normally. So we can actually put this one a rising edge. Is when the switch is pressed. And have the Y0 here. We have to latch it so that it can stay energized, because let's come. We switch. That's my press. So all we need to this is part art. So there are two sides of the large. Large is led to the air, which 5, 4, which means for the large, this floating wing has to move towards this end by the large pattern. 5 has to reset 4. In the two cases for large and small. Now we can see that the sensors are in. For large, all the sensors. Yeah. It's for the large now. At that time, all the sensors. Once they are energized, floating wing set by 5. Let's do for the small set for the small the X3 closed. That's for the small. X3 will be normal. In this case, let's F4. So we switch. Okay. this will set. I just do that again. For the sense. Okay, so here is a traffic light example. You have Y0 for red, Y1 for yellow, Y2 for green. So let's see what is being requested here. It says when PB1 X20 on the operation panel is pressed, the process is started. So first, the signal lamp red Y0 is lit for 10 seconds. So with X20, Y0 should come on for 10 seconds. So this is a timing issue now. So, and we know that X20 is a push button, and that should output into Y0. So, however, Y0 should be on for just 10 seconds, so we need a timer to be on this run as a normally closed contact, and the timer should count with this output. So T1 A 100. So here we just have to link these two output together, so that once Y0 is energized, T1 will be energized and the timer will keep counting. So K100 has 10 seconds, and because T1 here is normally closed with X20, so we need to latch Y0 here so that it will stay energized even when we have released the push button. So Y0 will stay energized. However, T1 is taking precedence, so that once the timer has counted to 10 seconds, K100, the T1 here would change state, which will cause this line to be de-energized. So let's convert this and write to PLC, and let's see how the red would behave. So once we push in the push button, you can see that the red is on and the timer is counting. So we'll see that once that counts to, we can see that the timer has stopped the red. So let's go on. So when Y0 is extinguished after it has been lit for 10 seconds, the signal lamp yellow Y1 is lit for 5 seconds. So yeah, after the red has gone out, the yellow should come on for 5 seconds. So here we can just use the timer T1. We can use T1 for 10 seconds. So we can decide to run this into a relay, relay M1. However, this timer will only be active for a momentary period, because it will only go energized and go off. So we need to latch M1. which is a relay in this case. So we latch M1 so that M1 can stay energized. Then M1 will be used to start the yellow lamp. That will be M1 running into Y1, and Y1 should be only active for 5 seconds, so we need another timer that will stop Y1, that's T2, at the end of 5 seconds. Insert a line here, so we need to add the timer to this output, T2 K50 in this case. So T2 K50, and we add this line here. Then this one stays energized here, however T2 would put it out once this time has been reached. Let's convert this and write to PLC and see how the system will behave. So we start with X20, the red is on. Let's see what will happen after the time for red has been reached. We can see yellow is on now, and let's see what happens after 50 counts. So we can see that the yellow now is staying on because M1 stays energized. So we need to find a way to stop M1 from being continuously energized. So let's edit this ladder. So what we can do here, simply we can remove M1 from here. Do not latch M1. Let's just cut this latch. So M1 is here momentarily, then we just attach Y1 here as a latch in this case. So let's convert that and write to PLC. And let's see how the system will behave again. So you can see red, then after the 100K number, yellow is on, and let's see what happens. So you can see now that the yellow and red is working fine, because after the 5 seconds the yellow has gone out. So let's edit again and see what is left to be done. So after the Y1, which is yellow, has been extinguished for 5 seconds, then the green, which is Y2, is lit for 10 seconds. So this same arrangement can be used, and just let me delete this line. So we have T2 into relay M2, and M2 now will be used to start the Y2, which is the green, M2, and that should come up for 10 seconds. So T3 as normally closed, so M3, Y2, which is the green output, and the T3 timer should count with the green, so that will be T3 K100. We just add these two outputs together, and we need to latch Y2 here so that I can stay energized, because M2 will only come on momentarily. So Y2 is latched. So let's see, write to PLC. So let's put the lamp on by using the X20. You can see the green is equally on, and after 10 seconds the green would go off. You can see. So here it said that the operation starting from 2 above are repeated. So which means after the green has gone out for the 10 seconds, the red should come on again. So in that case, we need to find a way to use the output of the green to start the whole cycle again. And what we can do here is to edit this and use the timer T3, which will go on to be energized momentarily here, and latch it with this first run where we have Y0. So what we can do is to have another relay, down here. So T3 into relay M3, and we'll be adding M3 here, insert a line here, and latch M3 with this Y0, so that when T3 here has counted for 10 seconds, the T3 here would deactivate, so this run will stop and the T3 here will be energized, which will cause M3 to be energized momentarily, and the same M3 will be energized there momentarily. However, because your Y0 here has been latched, this system would continue to stay on. So let's see that. So when you push the X20, you can see the red is on and the timer is counting. So after then, let me just restart this. So you can see the green, you can see the red again. So after this, as you can see the yellow now, then the green, and the cycle keeps going on like that. Okay, so here is another example of an industrial use case. Here you have the robot arm with supply command Y0 and the robot arm at starting point as X0. Then you have the conveyor forward Y1, and there's a sensor here which is X5. Then you have a supply of orange command as Y2, and X1 for box on conveyor, and X2 orange supplied. So let's see the control objective so that we know exactly what is requested in this case. So the overall control states that when the switch 1 X24 on the operation panel is turned on, the conveyor moves forward, and when the switch SW1 X24 is turned off, the conveyor stops. Then it says when X20, that's PB1 on the operation panel, is pressed, supply command Y0 for the robot arm is turned on, and supply command Y0 is turned off when the robot has moved from the starting point. So we can start from this second control level, so that the parts will be supplied on the conveyor before the conveyor begins to move. So it says the conveyor should, the supply robot arm should stop when the push button, when the arm has moved from the start point. So we need to use the starting point sensor on the same run with X20. So in this case, we'll be making X20 a rising edge so that it's only when the switch goes from 0 to 1 that it's going to be energized. So this is, we'll make X20 a rising edge, so that it only detects when the switch goes from 0 to 1. Then X0, which will be energized when the arm is at the start point. Then Y0, which is the arm itself as the output on this run. But for this run to be activated, we need to latch Y0 because X20 here is only a rising edge. So we need to latch it so that Y0 will stay energized when we have released X20. So we're latching Y0. So with this, we have dealt with this second objective. For the first one, we have the switch X24, which will be normally opened because it's a switch X24, and that would run into a relay, so that just have, so the relay can be, let me say M0 for the relay in this case. So M0 will now start, M0 will start the conveyor, which is Y1. So if you convert this and write to PLC, I will see that we have dealt with these two. So once we press the push button X20, you can see that the arm will supply a part on the conveyor. And when X24, which is the switch in this case, conveyor moves forward. So if you put the switch off, the conveyor stops. So let's see the other levels of control that is required. It says when the sensor for box on conveyor X1 in the orange feeder is turned on, the conveyor stops. So X1 should stop this conveyor. So then 5 oranges is placed in the box. So that means we have to count 5 oranges into the box. Then after 5 oranges have been loaded into the box are carried to the tray on the right. So after the 5 oranges has been dropped in, then the conveyor should continue moving. So number one, we need to stop this conveyor with X1. Then after 5 counts of oranges, the conveyor should continue. Then here it says oranges are supplied when supply command Y2 is turned on. So when the conveyor stops, Y2 should be activated so that oranges can be supplied, and number of oranges are supplied are counted when X2 is turned on or is set on. So X2 will use as the input for the counter, while X1 will use to stop the conveyor, and also X1 will be used to start Y2. So let's see how that will be done. Edit again. So number one, we need to stop the conveyor with X1. So to do that, we only need X1 to take precedence over X24. So I can come here and change this one to normally closed X1 so that current will flow. Current will flow on this one since this is normally closed. However, when X1 is energized, this will cause this to be energized and the state will change, because I'm using a NOT logic in this case, so that regardless of the state of this switch, current will no longer flow on this run. So this relay M0 that is controlling the conveyor belt Y1. So we have achieved the stop of Y1 with this, and it says oranges are supplied with Y2. So we need to use X1 to start Y2. So X1, when X1 is activated, so that will run into another relay, which in this case I'm using M1. So M1 will be used to start the conveyor the supply command of oranges of Y2. So that will be M1, M1, Y2, M1, Y2. So once X1 is energized, M1 will be energized, M1 will be energized here, and Y2 will be energized. So oranges continues to drop. However, we need to count the number of oranges. So it says 5 oranges are counted. So we need a counter in this case. And after the 5 oranges have been counted, the supply command Y2 should stop, which means on this run of Y2, the counter will be there as a normally closed, so that current will flow until the counter has fully counted the 5 number of oranges. So, and the input to the counter is X2, because we are told here that orange supplied are counted when orange supply command orange supplied X2 is set on. So X2 is the input into the counter, so we use X2 to serve as input to the counter. So X2 into C1 A5. So with this, and I want to use a falling edge here, so that I want to know exactly when the orange actually drops into the box. So that will be a falling edge detection in this case. So if we write this and we run this we run this into the PLC, let's see how the PLC will behave before we continue the other levels. Now I'm pushing the push button X20. You can see here that the box is supplied. When the conveyor is switched on with the X24, the box is stopped here and the counter is counting. Okay, the supply command Y2 So you can see that 5 has been counted into the counter, and once that is done, you can see that the counter has been de-energized here. So that's why there is no current flowing into Y2 anymore and no oranges is being supplied. So once you put a counter up, you need to always put up that to reset that counter, so that this 5 here will go back to 0. However, we are told here that after 5 oranges has been counted into the box, it is being carried to the right tray here. So the conveyor needs to be started again after 5 oranges has been dropped. So in this case, we need to use the counter to start this conveyor, to start this run of line 5 that we have here. So what we need to do in this case, because to start this conveyor, we need the counter to run into a relay. However, we also need to have some kind of output that we can control, so that once the boxes or the box has been dropped here, the latch that we're using to start back the conveyor should go on to be de-energized, so that the conveyor will not keep running repeatedly. So in that case, we could just edit this, then add another run here where we have the counter. In this case, I'll be using the counter as a rising edge, so I only want to know when the counter goes from 0 to 1. That's at the time the counter has already counted 5. At that exact time is when I want this to start. So I'll be using a timer just so I can have some level of control, which here will be a normally closed. I will explain in details why I'm using this. Then the relay is okay, we have used M1 already, so M2 in this case, M2, and I'll be latching M2 here, M2. Now why I will have to latch M2 here is because C1 here is a rising edge, so after 5 has been counted, C1 here will go from 0 to 1 momentarily. So because of the latch here, this run will have current flowing through it. Then I need this timer to count just for maybe some microseconds, and after then I want the conveyor to be started again. So I will attach the timer to this M3 K1 T1 K5 just for a few seconds. After the 5 oranges has been counted, I just want the conveyor to just hold on for like a few seconds before the conveyor starts to run again. So this timer here will get energized after K5 has been attained. So I'm going to be using that here, and with X5 as normally closed, this is X5 here, so that once the carton has gone past this X5 sensor, the relay that will be used to restart this conveyor will be de-energized, so that the conveyor will not keep going endlessly. So X5, which will run into another relay M3 in this case, M3, and I'll be latching M3 because I'm latching M3 here because this T1 will only be activated momentarily. Once K5 T1 has been attained, T1 here will change state, which would cause this run to be de-energized, and T1 here will be energized momentarily. And because M3 is latched here, current will keep flowing. So I will use M3 to restart the conveyor. Let me just insert a line here. So I'll be latching M3 here, M3 with this. So what will happen is, after the counter has counted 5 and it comes here to get energized momentarily, and the timer here is normally closed, so current will flow because M2 has been latched, so that the timer can count for the few seconds, this K5, and after which the timer will come here to be energized momentarily. And because M3 is latched and this is normally closed here as X5, current will keep flowing so that this conveyor can keep running. However, once the box should cross this X5 here will change state. So once it changes state, then M3 will be de-energized, so that this M3 here will also be de-energized, so that this conveyor will not keep running endlessly. And also for the counter, we need to reset the counter. So I'll be using X5 also to reset the counter as a falling edge, because I actually want to know when the box has dropped into this tray. So X5 as a falling edge, then we'll reset RST C1. So once the box has crossed X5, C1 will reset and the whole system returns to the way it was initially. So let me write this to the PLC and let's see how the system would operate. So press X20, the box is supplied, the conveyor is running with X24, so that will stop, can see here that the counter is counting 2, counts 3 until 5. Once 5 has been counted here, the counter here would be energized momentarily since it's a rising edge. Then M2, because it's latched, will cause, so the conveyor will continue and de-energize. You can see just one again. So it will stop the conveyor just momentarily after 5 has been counted here. This time I will just count for a few moments, so the conveyor will continue with M3. However, once the box should cross the this system is hanging here, so it's counting 3, 4 and 5. So it continues. See that will go energized to stop. So that's for So with that, we have come to the end of this session of programmable logic controllers. So for your questions and comments, you can send them to the link below. Thank you for your time.